we
About what?
I had a quick doubt about why we can pretty much like not care about the indicator function that x has to be between 0 and 1. Is it
Oh,
maybe because for the MLE we observe a sample already, and we can assume that the x's are in the correct range already, or something like that?
okay.
I'm not.
That's a great question. The reason we didn't put I didn't put indicator function here is because the domain is independent to theta. So this is independent to theta. So so and we can assume that the domain just in linear to 1. So the indicator can always 2.
Okay, I see. So because I guess because the likelihood function is actually a function of theta
Yes.
given some x. And then maybe what we do need to check is that the estimate that we find for theta lies in this interval, in 0 to infinity, right? It cannot be negative. So this
Oh
one we
yeah,
need.
yeah, yeah, yeah. So we should, yeah, in this case we have to put indicator for theta. Yeah. Yeah, you're right. So what indicator? Okay. Yeah, thank you. Yeah. And okay, so we can check this. This one is always positive because the log si is from 0 to 1. So log si is negative. So this is positive. Okay. So the solution is in the domain. Okay. So theta hat is yeah, so maybe I write more. Okay. Okay. So here we have 3 possible candidate for the maximum point. So first is candidate. Okay. First is theta hat. The second one is a boundary. And there are 2 boundary. One is linear and infinity. Okay. Okay. So what if theta is infinity? So I think this one we don't have to care about infinity because so if theta is infinity, then okay. Okay. So from the first we can check the second derivative. So that means yes, that's true. So this is candidate. So we find that this is negative, so it's concave. And theta hat is not is is in 0 to infinity. So theta hat is the MLE. Okay. Concave is not in none. It should be strictly concave. It should be. It should be strict. And it is strictly concave because it's smaller than or equal to 0. Okay. Concave is can be 0, but here is strictly equal to 0. Strictly smaller than 0, so it's strictly concave. So it's the maximum cannot in the boundary. Okay. So 下is MLE. Okay. Yeah, thank you. The maximum that can be out of boundary. Okay. Yeah, Albert, you are right. So we retrace based on the 0 to infinity. So if the maximizer is out of boundary, then maybe look at this. So we look at this. See the head? In this case, oh, sorry, it's not. Yes. In this case, the maximizer may be 0. Okay. Yeah, thank you guys.
What would the picture look like where it's concave but not strictly concave, and so we need to check the boundary?
Okay. So if this one is 0, then they may look at the line. That means
I see. Okay.
yeah, this is a constant, so it's a line. So you should in the boundary. Yeah.
Thank you.
You're welcome. Okay. Okay, and the next is the what's that? Okay, the variance. Okay. This theory we haven't learned, but I think you know that in the 310 or something, this can be approximate by the normal distribution and with the I theta inverse, with the official information, inverse official information. Okay. So from this, we can know that it is the variance of theta hat go to 0. I think we can also use this. Okay, let me check. How about we go to second question first? Yeah. Part B is the mass of moment. The mass of moment. Okay. So we want to find this. It's equal to x theta x to theta minus 1 dx from 0 to 1. Okay. Yes. Okay. So this is equal to 0 to 1 theta x theta dx. And this can be theta plus 1 x theta plus 1 0 to 1. Yes. Okay. So this is equal to theta plus 1. And the mass moment we have to use the S bar to approximate the population mean. So this is equal to, okay. And we can softly to get the S bar plus S bar theta hat equal to theta hat. And it can imply that the theta hat is a S bar divided by 1 minus S bar. Okay. So this is Mason moment. Okay. Okay, so next is question 1. And 30, so we had 45 minutes. So okay, now please do the question 2 and 3. The question 2 just use the definition of a list. And we have two estimators, S bar and this. And the third question, you have to use the definition of a mean square error. And you have to compare these two estimators, which one is better.
Hi, Chi. Could you quickly go over how you computed the variance in the first problem?
Variance?
Yeah.
Oh. Okay.
Okay, could you quickly please tell what the theta naught and the variance inside the normal distribution is?
Okay. Okay, so See, you all learn this theory. Basically, is we know that this is an exponential distribution, an exponential family, and from this, we can apply a theory of the MLE, and we can know that the square root of the estimate of MLE minus the true theta will converge to a normal distribution. Okay.
Did we see that in lecture, or is that something new that we're learning right now?
Yes, we haven't seen in lecture, but I'm thinking we may can use another way to find the variance. This can find variance of t. Okay. Okay, let's try another way. Okay. So without using the okay. So I think the main part of this question is that this is theta head is okay. Okay. We know that this one, the variance of this one will converge to 0. Okay. So what we can do is like this. We know this will converge to this. Take the square root of this. Lower the variance of this. This is just by the central limit theory. But if we want to find this theta head minus theta 0, okay. We can use a delta method. Okay, so this is a function. So we can think that this is a function of this minus the function of exploitation of this. Convert to this. Okay. And this will convert to a normal distribution with the derivative of this, plug in this value, and square, and the variance of this variable. Okay. So this is equal to, you can use the like the mean value theory is equal to G prime exponential of this, and multiplies the summation, the difference of value. Okay. And this one converted to a normal distribution. So hence the normal, and if it's a normal distribution, multiply a constant, you will become the normal, the variance will multiply the constant square. Okay. And we plug in G is equal to X. So this is another way to signal the theta have the square root of order is square root of n. So hence the values will convert to 0. Okay, we need to first find out the distribution. Yes, you can find the distribution of theta, and then you find the variance. Yeah, but usually find the distribution is much harder than just find the variance. Okay. Yeah, that's a way to do that. Yeah. Okay. Okay, does it make sense? Yeah. Yeah, you're welcome. And let's go to question 2 and 3. Okay. The question 2. Okay. We want to find a list. So okay, so the list is a mean square error in this case because it's a square error loss. Okay. So we have a distribution is this is a Bernoulli distribution. So now Bernoulli theta. The first estimate S bar. Okay. So we want to find the mean square error. The definition is S bar minus theta. How about I use the notation of S bar theta square and average. This condition of theta. So and this just the values of X bar. Okay. So we know the values of X bar is equal to values of X. And this is a Bernoulli, so it should be this. And the second one is this. Okay. Okay. So our T little theta definition is T little minus theta square T little X. Okay. And the T little only have 3 possible outcomes. So that is equal to 1 if the probability of summation, but the sample size is the number of the SI is greater than how about I use this summation of SI larger than n divided by 2. And if value is little, if the summation of SI smaller than 2. Okay. 1 over 2, okay. And the next one is 1 over 2 if the summation is x equal to n divided by 2. Okay. And this is a binomial distribution and theta. So we know the probability. Okay. So that's the answer. Okay. Okay, this is question 2. Any questions so far? So they just follow the definition. Okay, and okay, 3. 3, we have the S1, Sn. They are exponential theta. Okay. So the density is, look at this. And we have two estimates, S bar and C S bar and CS1. Okay. And we want to find the mean square error. Okay. So for the S bar, the mean square error is the RS bar theta is equal to S bar minus theta squared. And we know that the mean of S bar is equal to theta, so this just equal to variance of S bar, which is equal to square. Yeah, the variance of yeah. Okay. Okay. Yeah, C is secant square. Yeah, it's secant square. Okay. And the second one, the estimate is CX1. So here we have to be careful that the S1 is follow the exponential distribution of theta divided by n. So it may have a bias. So this is equal to C. So this is it's not equal to theta. So the mean square error may equal to the variance term of CS plus the bias term. So the bias term is this minus the theta square. So we have two terms. For the first term is we can use the property of this. So it should be C square. Variance is sigma square n square. And for the second term is just the variance. So it's a bias, so it should be C theta. Okay. So this is a function of C. So you can see it's a function of C. So if we want to find the best C, we can find the derivative of C. Okay. So it can be 2C theta square n square and plus the 2C theta divided by C is okay. Now we can solve this. equal to 0, then we will may get the what do we have? Okay. Let me check. Okay, the C should be n over 2. Okay. Okay. Then we can plug in the C. So maybe we say it's a C star. G C star is equal to okay. Let me see. Where did I calculate this? Okay, I think I have to do that. So it should be n squared 4 sigma square n square plus plug it here. So it should be sigma divided n minus theta square. Cancel these two. So it can be sigma square 4 plus 4 equal to 2 square. Okay. So you can see that the base one is n divided by 2. Yeah. Cx1 theta is equal to sigma square over 2. And for the S bar is equal to n. So we can say if n is greater than 2, S bar is better. But if n equal to 1, this one is better. Okay. So this conclusion. Okay. Okay. Does it make sense? Okay, so now please try to do the question 4. And in question 4, you want to find the base estimator of theta. And so this formula can hold for any prior. And try to derive this formula. Okay. So you have to find a posterior distribution.
Chi-Shian?
Hi.
For problem 3, did we find that the sample mean is better only if, or the sample mean is best if n is at least 2?
Yes. So
Okay. And if n is 1, so that suggests that we should just take, so that means we're just drawing one, there's just one observation. So we should just take, our estimator should just be 1/2 of that observation,
yes, that's
as
interesting.
opposed to just taking the observation.
Yes.
Okay.
Yeah.
Why would that do better? Like if the mean of the exponential is equal to the parameter, why would we want to take half of the observation?
So yeah, that's interesting. The reason is we combine the bias and variance. So if S1 divided by 2, the variance will decrease. Also, the bias will increase. So and we want to minimize the mean square error. So we want to find the, how about I say that? So if so we want to find which constant can make this combination, can minimize this combination. Yeah.
Gotcha. So it improves on variance, but is worse for bias. Okay.
Yeah. But for average, so if you consider mean square error, it can have a better performance. Yeah. So sometimes we may not want to use the unbiased estimator. So if you can make the estimate have some bias, if you can allow they have some bias, and we may have the better solution. Yeah. Yeah, that's a great question. Yeah.
Where is P of X in the formula? What is that?
Okay, this one. Okay, so sorry, here's P. Okay, okay, this typo, this PX. PX is modular distribution of X bar. So
So it's the log of P of X in the formula?
yes, it's not PX.
Okay.
Okay, let's go through the next question. Okay, so we have S1, Sn, they are normal distribution, theta, sigma square. Sigma square is known. So in this case, the pi is pi. It's pi. Okay. Want to find a base estimator. Okay. First we have to observe that the S bar is sufficient for theta. Okay. So for the positivity, we only have to find the theta condition on S bar. Okay. 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 So the Tx should be this. And this one is equal to indicator of theta and the posterior distribution pi theta condition on S bar equal to x d theta. And this posterior distribution is equal to like the pi theta multiply the distribution of x condition of theta divided by the distribution of x. The module distribution of x. Okay. So we may have this and this equal to theta and pi theta. This one is the distribution of S bar is follow theta sigma over. Okay. So the distribution is equal to exponential 2 pi sigma square n exponential negative 2 sigma square n x minus theta square d theta. Okay. So okay. And we can move let's move this constant out of integration. And it can be look at this px. Okay, here we want to do things like this. Theta minus x exponential okay. So we want to plot another x. The first is this one. Okay. This term is equal to density of x conditional theta. So that means this term is equal to px. Okay. So for this term is equal to x divided by px integration of f theta condition on x pi theta d theta. So from the definition, this is px. So the whole term is x. And the question is this term. Okay.
Can you
So
go
here,
over that one more time? Sorry, I wasn't able to follow the calculation.
oh,
Can you go over the last step you did just one more time?
okay, it's fine. So how about we do this? So this is 2 pi sigma 1. Okay. So this term is the density of the S bar condition X. So PDF of S bar condition theta. Okay. So it's a normal distribution. Okay. So and so we can have you can have this. Okay. And so this term is equal to the probability of x, the theta, joint distribution of theta x. So if we integrate over theta, you may have the modular distribution of px of x. So it can be the px divided by ps. So it should be x. Okay. Okay. And so now we focus on this term. Okay. This term is the this term is you can find this dx of exponential.
Did you mean to write f of x given theta?
You mean this?
The line above, should that be f of theta given x, or should that be f of x given theta?
Okay, so here I only use x is because we only have to find the distribution of this. Okay, so I use the s bar equal to x. So maybe I should write it on like the s bar equal to x. Okay.
But why is that equal to f of theta given x bar is equal to x? Where did that come from?
You mean this term? This
Yeah.
term. Okay. The s bar condition of theta is the normal distribution theta sigma over n. Okay. So at this time,
Right. So shouldn't it be f of x bar given theta?
S bar given data. Okay. Okay. What do you mean? Can you say again?
I'm sorry. I just don't understand why is it f of theta given x bar is equal to x if you're saying that. Where's okay? Maybe I'm just not following the calculation.
This one I represent the density, the PDF, the density of the Oh, okay, sorry. It's my mistake. So it should be.
Yeah. Okay, that was what was confusing me. It's
Yeah,
x bar given theta.
yeah. Sorry.
Okay.
Yeah, sorry. Okay, you're right. And the very
Okay.
last day is we figure out this term is have a relationship of the derivative of this. The derivative of this exponential will be equal to the exponential. The same term is here, but here we have the s minus theta and theta square negative n. Okay. So this term will be equal to px n sigma square, and so I shouldn't move this constant off integral. Okay. So dx exponential okay, and this is equal to px n, and this term we change it to the density of the f again. Okay. And we can move the derivative out of the integral. So it will be dx integral of this term. Okay. And this term is equal to p of x. No. This term is p of x. So we may have the theta square px n dp of x dx. And this is equal to log px dx. Okay. So we combine these two terms and we can give our formula. Yeah. So the tx is equal to x. Okay. Okay. I think that's today's discussion. And if you have any question, feel free to let me know. Okay.